Okay, so this this is a course on quantum field theory, anomalies, condensed matter. So I first start with some words, okay? As usual in a course, we start with some words, okay? What is this all about, okay? So first of all, we try to understand that these three words: quantum field theory, anomalies, and condensed matter. Okay, the relation between them. So first of all, what is quantum field theory? So who of you got a course in quantum field theory? Raise your hand. Okay. Who of you knows the Dirac equation? Who doesn't know the Dirac equation? Who is uncertain about whether he knows or he doesn't know the Dirac equation? Okay, that's a good point. No, fantastic. I was expecting much worse. Okay. So what is quantum field theory? Well, quantum field theory is quantum mechanics, okay? Okay, so probably I'm saying trivial things. So, okay, so who knows what anomalies are? Raise your hand. Okay. Who knows how to use anomalies in condensed matter? Nobody. Okay, okay, fantastic. So, so what is quantum field theory? Well, quantum field theory is quantum mechanics plus special relativity, okay? And when this is important? Well, it is important because, you know, you can transform energy and particle into energy. For example, E plus, E minus going to gamma and vice versa. So quantum mechanics is not good by itself because it applies to particles. So the particle number is conserved. But in this case, the particle number is not conserved. Only the charge is conserved, okay? So when this is important? Well, it's important high energy, of course, when this process takes place. Is it important in condensed matter? Question? Answer? Who want to answer? Okay, don't be shy. There is no price attached to this answer, so don't expect too much, but okay. Do you want to answer? Not really. Well, what is important? It's important when this process can take place, okay? And when this process can take place at low energy, when the mass of excitation is small, okay? Because yes, this energy has to do with the mass, okay? And the mass of the particle should be small. So if the mass of the particle or quasi-particle is small, or possibly zero, then this process can take place also at very low energies, like, I don't know, 1 Kelvin, okay? You don't need to go to high energy physics, okay? So it's in condensed matter is important for massless excitation or say quasi-particle or quasi-particle, okay? So sometimes you start from a condensed matter system where basically everything is written in terms of electrons, but then you have a low energy, if you have some quasi-particle in some condition that are in fact massless, okay? For example, of course, phonons are massless, but there are also, this is not really applied to what we're going to say because they are bosons. So we are interested in massless fermions excitation because these anomalies have to do with fermions, okay? So in particular, what we are going to use this is topological state of matter. So fermion, massless or gapless, massless fermions, okay? Topological phases of matter. In the simplest case, topological phase of matter is characterized by massive, it's a system, let's say, I don't know, some volume, okay? and inside you have a massive, large mass. Basically, there is no excitation. But on the boundary, you have massless fermions. That's a typical situation, okay? So you have massless fermions. Massless fermions must be described by quantum field theory, okay? Okay, so what is okay, that's the first argument. Second argument, what are the anomalies, okay? The anomalies. Anomalies, the name says that something went wrong, okay? For example, you have a car and your system says blinking. That's an anomaly, okay? But in fact, this is a historical name and it's not a problem at all. Actually, it's a very interesting phenomenon, as we shall see. And the fact is that anomaly means that non-conservation or if you want current, or if you want symmetry, diciamo, losing a symmetry at quantum level. Okay, anomaly is this, okay? So primarily it applies to fermion, to massless fermions, okay? So what is important? It's important because it's a quantum relativistic effect, so it's something that takes place in the quantum field theory, okay? Field theory, and also it's important because you may have it's a low energy effect, so it has to do with massless fermions, and so it's a low energy effect. Okay, low energy effect, and so that means that if you have a system, a condensed matter system, which develops massless fermionic excitation, you may develop an effective description for low energy, for example, near the Fermi surface, small fluctuation near the Fermi surface, and then this system can be characterized by this phenomenon, which is in fact. It is in fact is exact effect independent of dynamics. It's an infrared effect which is independent of dynamics. Okay? How is this possible? Well, it is possible. Okay? So, and in fact, sometimes this is important because this effect implies in the condensed matter theory. Okay, condensed matter theory, you have, as I said, an effective condensed matter theory. You have an effective description for energy near the Fermi surface. Okay, effective description. This effective description, if you include in this the results of anomalies imply universal response of the system. Universal, exact, and sometimes you also say geometrical, because it has to do more with geometry than dynamics. Okay, this thing will be clear later. It's not immediate. Okay, It will take some time, okay? And so this is because it's universal that can be used to describe robustness of some phase of the system. Okay? Another word which we use is topology, topological. What does it mean, topological? Do you know? Who knows what the word topological means? Yes, that's one aspect. Okay, the first instance of this word is that is something which is dependent under smooth deformations. Okay? So, for example, a potato is topological equivalent to a sphere. Okay? So something which is dependent on smooth deformation. This smooth deformation can be smooth deformation of space, of a certain gauge field, some background, smooth deformation of the Hamiltonian, smooth deformation of some parameter, something which is independent of these smooth deformations. Okay? Is this possible? This possible? Yes, it is possible. That's the beauty of it. Okay, it is possible. We will see. Okay. Amazing, no? Amazing. You've been taught that first everything depends on Hamiltonian. First credo that we are going to destroy or change. First credo that something depends only on Hamiltonian. Given Hamiltonian, no, there are properties that depends that are the same under smooth deformation of the Hamiltonian. Until, for example, you arrive to you go to a mass to you if you have a gap phase, and then if you go to the critical point of course mass goes to zero, gap goes to zero, so then it changes. But within the same phase, when the gap, you can have properties which are independent of the Hamiltonian. Okay. Or independent of certain property of the gauge fields. If you apply a gauge field, something is independent of the gauge field, okay? And also that's the first thing. And the second thing is about geometrical. So that, okay, that's the same thing. Another thing is exact. So what does it mean exact? Exact means that something takes a certain value independent of everything. So you have been taught that usually you have nice Hamiltonian, and then this nice Hamiltonian is spoiled when you go to a physical problem because you have dirt, because you have impurities, because you have a background effect, because you have such, and then you say, oh, so sorry that this Hamiltonian was so nice, but then the end, the result is so dirty that it's not so nice. Well, this is a case in which it is exact. It doesn't depend on disorder. It doesn't depend on all possible accident that you find in your life, and it's independent. It's fantastic thing. It's fantastic thing. I hope I will be able to convey you that it's fantastic thing. Okay. 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 I said this. Okay. Then you say, well, but in condensed matter. In condensed matter, I don't have in this. I don't have a relativistic theory. So condensed matter is non-relativistic. So condensed matter is non-relativistic electrons. So how this did no anomalies, okay? No anomalies. So how is this possible? Well, it's possible because in the end, if there is an anomaly, so this phenomenon of a massless particle, it is present in a subsystem or in a certain specific description of the system, and then somehow in general it should cancel, okay? So there is, globally, in the whole system, anomalies should cancel. And that's also another fact that's interesting. So you have an effect, but then globally should cancel because overall this is a non-relativistic system. Instead, the property I'm discussing has to do with massless particle and relativistic theory. Okay? So that's a combination of words I wanted to say. Okay? Just to say something. Now we go to a simple example, otherwise these words will remain somehow empty. Okay? So the simplest example I'm going to discuss is free fermions in one dimension. Okay? Okay. Free fermion in one dimension. So let me take fermions in one dimension, and if you want, you can consider a circle. So it's one-dimensional system with periodic boundary condition, which is of length L, or if you embed the circle in 3 dimension, it is 2 pi r. Okay, so you have these electrons here, they move. Okay, and so they are free, or they can be on a lattice. It doesn't matter. You have a hopping Hamiltonian. Okay, and so so in general you will have an Hamiltonian of this form. Okay, where these are ordinary creation and annihilation operator of fermions. So we take a free theory. Okay. Okay. If it is so what do you do? You take a Fermi surface. Okay, and you fill up to a Fermi energy. Okay. And these are empty. Okay. 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 If you have a lattice, then this will be the form here. Okay. But it doesn't matter. It doesn't matter what I'm saying. Okay. Okay. So I have the momentum. Here I have kf, and here I have f. Okay. Then I expand. I also know that I take anti-periodic boundary condition for the fermions, which is standard for fermions. Okay, that you know, right? And so I will have that momenta are quantized in 2 pi over L n minus 1/2. Okay. So I expand near the Fermi surface here. Okay. Linearize around the Fermi surface. So I will have from one have kf minus kf equal to n plus minus 1/2 2 pi over L, and k equal plus kf equal to n minus 1/2 2 pi over L, and I say that n plus less than 0 is filled, and n minus bigger than 0 is filled. Okay? So my index is normalized, is redefined. My index is redefined to count 0 here. Okay, 0 here and here. Okay? So there are There are no on the line. The line is between an empty, Fermi surface is between an empty and a filled thing, okay? Okay, okay. So the energy is, of course, energy is Fermi energy plus or minus kf over m and plus minus 1/2 2 pi over L, and this is the Fermi velocity. Okay? That you know, right? You know? Okay? Okay. So let me do now a simple thing. Okay? I add an electric field. Okay? Add an electric field. Okay. How do I add this? Okay, I take along the direction of the line, AX, okay, which is equal to, and this is dt AX minus dx A0, okay? Okay? And then I take this, I take A0 equal to 0, I can take the gauge choice. And also in one dimension, I can say that AX of t can also be eliminated the x dependence. In fact, I can take it proportional to the time. So if you want to do an exercise, here's the first exercise. Proof that this x dependent can be gauged away. Okay? So I take a constant electric field just to, okay? Okay, now what it implies that the P goes into P plus AX, okay? And so that means that n plus minus going to n plus minus plus L over 2 pi AX. Just by this, okay? Okay? So what's happening? All energy levels move to the right. Like this. They move, okay? Because you see the number is shifting, okay? Number is shifting. The number n is growing. So basically all the levels with electricity, they move. Okay? And what is the net effect? The net effect is that on this side, an empty state, for example, will go after a certain time. An empty state will go below the Fermi surface. Here, electron will go up above the Fermi surface. Okay? Okay? So then it will be a charge for let me call this part the plus branch, okay, plus part of the spectrum, and here is the minus part of the spectrum, okay. Okay, so we will have that delta Q plus is proportional to delta N plus, and delta N is this, okay. And okay, so you see that the total charge is conserved, okay, because here you lose, for example, here you get a negative charge and here you get a positive charge, okay. So delta charge, which is delta Q plus Q minus, is equal to 0. But the difference between the two sectors, okay, that I will call twiddle or axial, or chiral, no, axial in this case, which is delta Q minus delta minus is different from 0, okay? So what is it? Well, is equal to the electric charge that I forgot to write. So I put here equal to 1, unfortunately. I put equal to 1. So sometimes I will put back the electric charge, but basically I use electric charge equal to 1, okay? But anyhow, at the end I will put back the charge. Okay, how much is it? Is delta n plus minus delta n minus, okay, which is 2 pi delta ax, okay, that I can write also 1 over pi integral between 0 and L dx dt dt ax, okay, okay, okay. Because I choose a time independent, I choose a space independent ax, but then in the end I can recover because this is a charge, so it is both a scalar in with respect to Lorentz invariance, and also is also gauge invariant. So I can recover, I can rewrite this equation in a covariant form, okay? And the relation is the following. So you can say that delta Q axial, okay, is integral between 0 and time of dt of Q axial, okay, which is dt dx of J0 axial, okay? J0 is a current, and this is also equal to double integral, d0 J0, d mu J mu, Twido, okay? Because the space component is a total derivative, but we have a periodic boundary condition, okay? And also I can write this 1 over 2 pi double integral, okay? And this is going to be gauge invariant object. I reconstruct it, and this is going to be epsilon mu nu d mu a nu, okay? Which is a scalar, relativistic scalar. So in the end, I can rewrite this effect in terms of a relativistic formula that there is a current which is not conserved. Okay? Okay. So the current is, conserved current is express the fact that the charge of the two branches, the difference of charge of the two branches is not conserved. Okay, what's the point? The point is that in the relativistic theory, so if you have a relativistic description of this fermion, okay, so you take a limit of very large number of electrons. This bottom goes down very deep, okay, and so then you are interested in the low energy description. So you take a range of energy around the Fermi surface. In fact, this system becomes relativistic. So the fermion become a relativistic fermion, and the Fermi C become the Dirac C, which is infinite. In the relativistic theory, these two branches are independent, and there is a conservation associated to each of them. So the anomaly is the fact that the conservation of each branch is not respected, but there is a non-trivial dependence on the applied field. Okay, so this is 1 + 1 dimensional chiral anomaly. Okay, so in the relativistic theory, so we have a Dirac electron. You have two independent current, J plus and J minus. And J, which is J plus J minus, is conserved, the total charge, okay? And J tilde, which is the difference, is also conserved at the classical level, okay? Okay? The anomaly is then the fact that one of them, the difference, is violated when you put an external magnetic field. This is a quantum effect that, okay, this is a trivial thing here. In this example, is a trivial thing, but in fact, it has a lot of interesting facts that we will discover little by little. Okay? So, there is no problem for the non-relativistic theory. You see, it's just that this effect is okay. So what? You say. So what? Okay. Well, we will see. So what? Okay. But in the relativistic description, you have an infinite Dirac sea. These two charges, the fermion decouples in two independent components. One is left moving, the other is right moving. Okay, they are both conserved charges at the quantum at the classical level, and one of the two, with difference, is broken presence of and this effect is a quantum effect. Is not present in the classical theory, and so it's called an anomaly. Okay. Understood so far, please? Please. We have to study the Dirac equation. They will come later, okay? I decided not to start right away with the Dirac equation, but I thought I was scaring you, but it will come, okay? Yes. We have to write the Dirac equation and see that at the classical level, these two are conserved. Somehow that is kind of obvious because the fermion split in two components. This is ultimately a property of the Lorentz group. So elementary particle is a irreducible excitation representation of the Lorentz group. And when the fermion become massless, it's split into parts, both in 2 dimension and in 4 dimension. They are independent, okay? They have independent dynamics when they are massless. And so they have an independent charge. Why not? But when this is a classical theory, falling from relativistic invariance. When you introduce a background, you have this effect, okay? Okay, so what has to do with, so what is special about this? Well, this is special. It's special because we will discover little by little that this is special, okay? And so it's not so trivial as I introduced to you. And in fact, is a kind of, there are some miracles underlying this thing. You know, for example, I have an example of this thing. When you, for example, you walk, you take a stroll in the wood, okay, and maybe it happened to you that you take a stone, you reverse a stone, and you discover that there is some life under it, okay? Something unexpected. For example, once I reversed a stone and I found a frog that was sleeping there, okay? Because hibernation. Maybe it happens to you, I don't know. Well, so that's the kind of thing. So this is type of thing. You have a dumb stone here, and then you open it and you say, there is something. I discover, I don't know, a diamond or a jewel, and so like a fairy tale that I don't know. There is I don't know. There is a young lady that she's a princess, but you really don't know yet, and then she will discover that under a stone there is some sign of his lover that will meet again, and these type of things. Okay, and so that's what we are going to see. Okay, little by little. Okay. So what is important? Important is this coefficient, 1 over 4 pi. 1 over 4 pi is exact. So it holds, this coefficient, it holds when you complicate the business. You complicate the story as much as you want, it will remain the same thing. Okay, so this is a response. You see, you apply the external field, you have a response of the system, the particles start to move. They move. The move is a collective motion, okay? Sometimes called, as you will see, the proper name is spectral flow. Spectral flow. They move, and collectively, they bring their electrons on top together. So, okay? So this is spectral flow. Okay? And this result is independent on how much you complicate the business. So let's see how is this possible. Okay? Okay? So let me complicate the business, okay? I complicate the business and I say, okay, let me consider when the spectrum returns to itself. So when spectrum return to itself. Well, when delta Q tilde is equal to 2, because that means that, you know, these move exactly here. So every moves to the next one. Okay? Exactly. So in the end, the spectrum is the same. But there was an effect that the electrons have moved. So the spectrum is the same, but the occupation in the move, the occupation has changed. Okay? Okay. So what is special about this? Well, I also consider okay, that's it. Okay. So delta AX is equal to 2 pi over L, okay? And so let them also me take a more general AX of t of the following form, f of t 2 pi over L, okay? And let me suppose that this is a ramp function, so a function which goes from certain interval minus t to t goes from 0 to 1. Okay? Any function, any ramp function goes from 0 to 1. Okay? Okay? So what is delta Q T do? okay, is 1 over pi dx dt. I use this covariant form, okay? I use the covariant form, so well, it is here, okay? You see, that here this is a total derivative, okay? So it only depends on the value of the a at 0 at the extrema, okay? Once it is rewritten in this form, okay, it is independent of the time dependence of a, only depends on the extrema. So in between it can be anything, okay? And that makes 2, okay? It's 2 in this form. Okay, that's it. And now I suppose that this is an adiabatic change. This I didn't say you before, but it has to be an adiabatic change. It has to be very slow. Otherwise, you could have, if it is fast, electron could be excited. So when you apply a fast thing, you could get excitation. So if it is very slow, the electron will not be excited. So they will follow the states in their little movement in one direction. Okay, so it's adiabatic. So T is very grand. It's very big. Okay, adiabatic. Okay, and now how can I realize this? How can I realize this? This thing? Well, a simple way to realize this thing is to imagine that you imagine that you have this one-dimensional system embedded in three dimension, okay? One-dimensional system embedded in dimension, and you put a magnetic field inside, so-called flux insertion. You put a magnetic field localized here in the interior, okay? So concatenated to the circle, okay? Then you say you can use the one of the Maxwell equation, which is okay, okay, okay. So then what is the what is the flux that I have to put to realize this? It's a slowly varying field flux which produces an electric field on the circle. Okay, okay. It is okay, and this is equal to minus 2 pi because it is the same integral. Okay, and so you get 2 pi. Okay, so let me write it. Dt L 2 pi over L dt f of t, and so this is f 2 pi f of t minus f of minus t, and so this is 2 pi. Okay, no, better to go on this side. Okay? And so we have arrived to the fact that the spectrum return to itself by adding one flux quantum. Phi naught, which is 2 pi, or if you want to put back the constant, it is this quantity. Okay? So insertion of a flux quantum does not change the spectrum of the Hamiltonian. Yes? You don't get it? You get the same spectrum? You see, no? Because this delta A was a change of delta. You see, 2 pi over L here means delta n plus or minus equal to 1 plus or minus 1. Okay? And so the spectrum returns to itself, you see?
One goes down and one on the left goes down and on the right goes up.
Yeah, but the spectrum is the same. You see, the energy levels, so
But the spectrum is initially symmetric.
it's the same. The feeling is different, but the energy spectrum is the same.
But the spectrum is symmetric. So one goes down, one goes up.
The electrons, the feeling changes, but the spectrum, okay? So, you know, you can also represent each of these lines, okay? So let's take a single branch, okay? Okay, so this is minus t and this is t, okay? It's happened that, okay, this goes to this goes to this, and this goes to this, okay? But then the spectrum is the same, you see? The fact is that if this had an electron, it carries the electron with itself. Okay, so the feeling is different. But the Hamiltonian is the same. Okay? So you can say pictorially you can say is okay, you can say that Hamiltonian plus a flux plus a quantum flux is equivalent to Hamiltonian without flux. Okay? In which sense it is equivalent? Well, it is a gauge transformation. With respect to Hamiltonian, it is a gauge transformation. Let me show you the gauge transformation. Okay, you take a mu of t minus a mu of minus t. Okay, it is d mu lambda. Well, so it's a gauge transformation where lambda of x is 2 pi over Lx. You see? So the two situations, this equivalence is up to a gauge transformation. Up to a gauge transformation. You see? Okay? Okay, no, we're doing fine. Up to a gauge transformation. You say, oh, but then if it is a gauge transformation, this is a property that is valid. This spectral flow is valid also if I complicate the Hamiltonian, because I can put interactions. I can put something that the spectrum are not evenly spaces, but somehow have a different structure. But after some time, I go back to the same spectrum. So the effect is the same. The energy change, okay? For example, one electron, suppose you put interaction. So one side, maybe the electron are closer spaced than the other side. The energy will change. but the charge, the net effect on the charge will be the same. Okay? So, just a second, then I answer. Okay? So, conclusion is that when you do the spectral flow, you come back to the same spectrum. If you imagine the system embedded in larger space, you insert a flux quantum like this. Or if you want, the Hamiltonian return to itself up to a gauge transformation, which is of this sort. Okay? This has a name. This result has a name. It's called Byers-Young theorem. It's not possible to distinguish the spectrum of two Hamiltonians which differ by insertion of a flux quantum. So theorem, okay? I derive you in a simple thing, but you can see many instances of this in many instances, okay? Let me give you, we will continue on this more and more and more, okay? Many aspects will come up, and then you will start to discover that indeed you reverse a stone and you find something special. I mean, the amazement will come to you little by little, not immediately, just little by little you will be introduced, if I'm good enough, to this amazement, okay? So let me give you a simple argument which is very instructive in itself, and then maybe I take your question at the end, okay? Because I finish in 2 minutes, okay? Let me give you a semi-classical argument, which is, in fact, not so semi-classical, but anyhow. Imagine that the fermion is not a quantum fermion, but just a test particle. So let me take that the fact, a shortcut, which is that electrons are just test particle. So it's it's kind of shortcut, okay? Okay. If I put this magnetic field, and I let the electron go around, okay, what do I find? I get the so-called Dirac phase. Okay, Dirac phase, which is e to the e over h integral of a along the trajectory that the particle did. Okay, you know what is a Dirac phase, right? Do you? No, you don't? And then you let the test particle go around this circle, okay, in presence of this magnetic field inside, okay, of this flux quantum inside, okay. Okay, what is a Dirac phase? Well, if you have a path integral, then you know that the coupling to the external field is a mu, j mu, and when you represent a j mu as a test particle, j mu is proportional to this, okay? It's okay, velocity. Or if you want the Lagrangian of a point particle has a term v scalar a, okay, which is a coupling. So this is v scalar a, or if you want in field theory is a mu j mu is the same thing, provided j mu is v mu, okay, ji is vi delta of minus the trajectory. That's another formula you can use, okay? if for example, if you have a wave function, and you put the wave function, you put an external field, the wave function will acquire this phase when you put an external field. Okay? So this is extremely important thing, Dirac phase. Okay? So how much is the Dirac phase if I have a flux quantum? If it goes around the flux quantum? Well, you see, you use you replace the circuitation of A as a flux, okay, and then this becomes e to the h bar c of a flux of B, magnetic field through the disk, such that the boundary of the disk is the circuit, okay? And then you get e to the e c phi naught, okay? And because phi naught is that thing, you get e to the 2 pi, and you get 1. Okay? Eh? Wrong? Eh? Phi naught is wrong? No, phi naught. Phi 0. Yes, phi 0. Dove? Questo? Non è phi naught, no? Dove ho sbagliato? No. Sorry. Okay? Sorry. Okay. Oh, see? You see? That the effect of a flux quantum is nothing. And so you understand that the spectrum is the same in simple terms. Okay? But in which sense it is? Well, in which sense is nothing? Well, it's not totally nothing, because the spectrum goes to itself, but the particle have moved. Okay? So this is a bit strange, and we will discuss this in the next hour. Okay? So what was your question? Eh? Yes? To 1? That's precisely the point I'm going to discuss in the second hour. Good point, yes, good point. While this is a gauge transformation, if I stop before it's not a gauge transformation, it's coming. Okay. So maybe you have a question, please. Yes? 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 And no, this is not the way to prove the theorem. It's not a way, it's just an intuition. Yes? 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 2 pi, yeah? Yes? 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 Because if you in a, I mean in technical term, the wave function of particle and the wave function of particle in presence of the gauge field is this phase for all the particle. For all the particle. The problem is what is actually the velocity here. The interaction will tell me the velocity, but I'm not using the velocity, you see? The velocity cancel because it becomes, you see, for any particle. So, for example, if you have that, if you have an Hamiltonian, if you do this transformation, the Hamiltonian, which is p square, will go into p minus ea square, you see, by doing this formal transformation. Yes, yes. And so for any particle, I will get 2 pi, irrespectively of the velocity, which is the issue of the dynamics entering the velocity, and whether they do go around or not. Okay, because interaction they might go around or not. Anyhow, the result will be the same. No, I don't connect. It's not that easy. Yes. 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 Another intuition is the following. You say that if I have a many body problem, okay. Nevertheless, the angular momentum, which is momentum on the circle, becomes angular momentum on the circle in 2 + 1 dimension, okay? And angular momentum is conserved independently of the interaction, okay? And so if you have a wave function which has some energy and angular momentum L, okay, then it has a dependent e to the alt theta, okay? And that will cause you L going to L + 1 because independently of the interaction. So another way to see that there is in this spectral flow, you can see that momentum goes up in one, okay, and if you embed the problem into a plane, then its angular momentum goes up in one, okay. Angular momentum is conserved, is independent of dynamics, okay, and so when phi goes to phi plus phi naught, you have this effect. So you return to itself, same with one extra value of the angular momentum. Yes, yes, it's a ground state wave function. Yes, so this spectral flow is a kind of current, but it's not an ohmic current. Okay, it's a collective motion of the ground state. And the process is also called the towless pump. If you want extra name, this is towless pump. Okay? Okay? So Towless had a bike and he had to use a Towless pump just to remember. Okay, so we continue after a break.